So these are questions from chapters 5 up to, I think, 14 or so. Basically going through intermolecular forces, acids and bases, solution chemistry, and then like the very beginning of organic. So we've got 5 molecules here. And the question is, what is the strongest intermolecular force involved for each one of those molecules? Which one should have the highest boiling point? In other words, which one is the strongest intermolecular forces? Which one would have the lowest intermolecular forces? So what is A? What is that molecule there?
When I look it up, Professor, it says it's ozone.
Ozone, that's right. Ozone is a particularly active form of oxygen, which we know is up in the upper part of the atmosphere, and it absorbs UV radiation. So it's very, very important. So what I would suggest is actually we should draw each one of these in order to give us a better idea on how what their intermolecular force could be. Okay, so let's start with ozone. I think we may have done ozone before, but let's see. So ozone goes like this. In a line. So how many, excuse me, how many total electrons should, valence electrons should ozone have?
$18.
18, that's right. So each oxygen has 6, so there should be a total of 18. So how many do we have in bonds right now?
4.
4. So we should have 14 electrons left. So as we usually do, we'll put them on the outside first and then work our way into the middle. So 2, 4, 6, 8, 10, 12, and then we have 2 left over, and they go in the middle, 14. So what are the issues with this particular structure? I see some problems with this arrangement.
Middle oxygen isn't happy.
Right, middle oxygen only has, how many total electrons does the middle oxygen have?
4.
It has 4 valence electrons.
4 valence and 6.
6 total, right, because it's got, each one of these is a pair of electrons. So it's sharing 4 and it has 2 for itself. So it does not have an octet. So what should we do with that?
Create double bonds, share a pair from each oxygen on the outside.
Okay, well, let's start with moving this pair. So now how many total electrons does it have? The middle.
It only has 5 valence now.
It only has 5 valence, but how many total electrons does it have?
It's 8.
It
But
does have 8, so it does have an octet. So, but it only has 5 valence electrons. So what does that mean if it has 5 valence electrons? What does that mean for that oxygen? Would it have a charge?
I think we have a charge.
Sorry, it would or it would not
It-
have a charge?
It would have a charge.
It would, right, because it's supposed to have 6 valence electrons, but it only has 5, so it would have a charge of +1. That's an odd thing for an oxygen to have. So how would we get rid of that charge?
Would it be 2 double bonds?
Okay, let's try that. Because the oxygen on the end, what would be how many valence electrons does that oxygen have?
Is that 7?
That has 7, right? It's supposed to have 6, but it has 7. So that oxygen has a charge of -1. So the suggestion is we take a pair of electrons from the oxygen with the minus charge and make a double bond, right? Is that what people want to do?
Let's try that.
Let's try it. All right, so we move that pair and make another bond. So now, how many valence electrons does the oxygen on the end have?
Six.
Now it has 6, so it no longer, so that doesn't have a charge. That doesn't have a charge. How many valence electrons does the oxygen in the middle have?
Four.
You're forgetting these
Is
two.
that 6?
It has 6 as well. So no charge there. So everything's hunky-dory, right? Everything's fine? Or is there a problem?
Isn't it fine because of the it was supposed to be 18 electrons
Mhm.
and they fit the 18 electrons.
Yep, we have 18 electrons total, so that's fine. There's no charge in any of the molecule, any of the atoms, that's fine. But I think there's a problem. Anyone figure it out?
Is it because they don't they break the octet rule?
That's right. The oxygen in the middle has how many bonds? Has how many electrons total?
10.
It has 10. Can oxygen do that?
I don't think it can it?
So you think it can or it cannot?
Cannot.
It cannot, that's right, because oxygen is in which row of the periodic table?
Second.
It's in the second, it's in row 2. So the most possible electrons it can have in its outermost shell is 8. It cannot have 10. So that is not possible. So unfortunately, we have to send those electrons back. So we're going to have to remove them and send them back to that oxygen on the end. So what that means is that this oxygen is going to have no charge. This one's going to have a +1 charge, and this one's going to have a -1 charge. And that just has to be the way it is. And what actually we see is we get sort of a sharing of a pair all the way across, but we never get, there's always going to be a charge somewhere. So we're going to have 2 charged atoms in this in ozone. with a pair of electrons moving. This pair of electrons basically moves back and forth and back and forth, always moving, trying to suppress the charge, but it can't because there's no way to do that. If it was sulfur, it would be easy. Sulfur can have 10 electrons, but oxygen can't. That's why it's such an active, chemically active molecule, because you have those electrons racing around. So that's
So
what
in-
oxygen's going to look like, or ozone, sorry.
So in this case, when writing or when drawing the Lewis structure for this, can it
Yeah.
just be a plus sign and a negative sign, or,
Yep.
and then
Yep,
you just,
plus and minus. Mhm.
and do we indicate it in a certain specific spot, or it doesn't matter?
Well, yeah, I mean, the basically there'd be more negative charge on the end than there is in the middle.
Well, no, I mean like top right or the bottom of it. It
Oh,
doesn't matter.
no, doesn't matter. Yeah, just show there's a charge. So what kind of intermolecular force would we have here?
It's a dipole.
Yeah, basically, I mean, you would think it would be ionic, but basically it's an extremely high dipole. Because unlike an ionic bond, these electrons involved in charge are always moving. And so basically what it means is you get an extremely strong dipole. So you would have very, very, very strong dipole-dipole interaction. Now let's look at neon. That's neon's. Oh, sorry, someone wanted to ask a question about that.
I was just wondering in terms of the axe shape, would that make it very like
Of the what shape?
the axe?
Oh, yeah, this would be bent,
Okay, so this would be like very polar then, right?
very polar.
Okay.
Yeah. So basically, yeah, it looked like this. So we would have a very strong, so you'd have sort of the usual dipole there and have a very, very strong dipole in this direction. Okay, so this basically, has a positive charge. So you have a dipole going in this direction, and then you have a very large one going in that direction. So basically the whole molecule would have an extremely large dipole pointing down. Okay, now neon, that's pretty easy to draw, right? Done. So what sort of intermolecular force will we see with neon?
Can it have a intermolecular force? Because
Everybody can have an intermolecular
okay,
force.
because it's noble gas. It's I
Mhm.
mean, yeah, it's a noble gas and it's stable. So I'm just wondering.
Still can have a intermolecular force. It's not very strong, but it still has one.
LDF.
London dispersion, that's right. So that would be pretty weak, right? So if we have neon, it doesn't really interact with other neon atoms very much. So that would be pretty weak. What about tetraiodomethane? What would that look like? Who goes in the middle? Carbon or one of the iodines?
Carbon.
Carbon pretty much always goes in the middle with 1, 2, 3, 4 iodines. We'll give them each a bond. So how many total electrons did tetraiodomethane have?
32,
Sorry?
32.
So each iodine has 7, so that's 28, and carbon has 4, that's 30, 32. Well, 28, 32, right? Yeah. Which is what you said. So let's 32 go around the outside. Wait a minute. Wait, oh, wait, we've already used 8 for the 4 bonds, and that leaves us with 24. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we're done. And that makes sense because carbon is making 4 bonds and it has no lone pairs. That's typically what carbon looks like. So what shape is this going to be? Use your Axe body spray rules. And what's it going to look like? So carbon's a central atom. How many bonding regions are around it?
Tetrahedral.
So it's got how many regions around it?
Oh, X is 4 and E is 0.
E is 0, right, because it doesn't have any lone pairs. And that is a tetrahedral shape. So what's going to be the polarity of this molecule? It's going to be polar or non-polar?
Wouldn't this be non-polar because it's kind of equal on all sides?
Right. It's completely symmetric. So it is non-polar. So it has 4 polar bonds because iodine is more electronegative than carbon. So each of these bonds has a dipole pointing toward the iodine. But since it's completely symmetrical, they all cancel each other out. So that would be a non-polar molecule. So what interactions would it have?
London dispersion force.
Yep, LDF for this one too. So D, what is that?
Now, is that aluminum
Yep.
with chlorine? Okay,
Mhm.
sometimes it looks like, just A and then I and then CO. So I just
Well,
need
is there an element called A?
I don't think so.
There isn't.
Okay.
There is no element A, which is
Oh, this
weird,
one's
right?
ionic.
There's a B and there's a C. There's no D though.
So this would be the strongest one.
So what's it called?
Aluminum chloride, I think.
Right. Just aluminum chloride, because we know what's the charge on aluminum when it's ionic. Excuse me.
It's always +3, right?
It's always +3. And it's got 3 chlorines around it. So what's going to be the LDF or the LDF, the intramolecular force for aluminum chloride?
Ionic.
That's going to be ionic. And then finally, what's this one? What do we call that?
Silicon tetrafluoride.
Mhm. Is it ionic or is it covalent?
It's covalent.
That's covalent as well.
So it'd also be another LDF, right?
Whoop, whoop. Oh dear. Oh dear. What happened? Everyone still there?
Yep.
We're
Man.
here.
Yeah.
Weird. If I tap just one part of the screen wrong, basically shuts my computer off. It is not a good Come on. There we go. Oh, weird. Okay. So silicon tetrafluoride. So that is going to be non-ionic. So let's see, but before we say it can only do London dispersion force, we really should see what shape it is. So let's draw it. So who's going to be in the middle?
As silicone.
Okay. So how many total valence electrons does fluorine? How many valence electrons does fluorine have?
Seven.
7, right? So there's 28 for the 4 fluorines. And how many valence electrons does silicon have?
4.
4, right? So let's see. So that's 4, that's 32. That sounds kind of familiar. So we minus 8 for the 4 bonds, and we left with 24. Damn, I was going to use sulfur. Let's use sulfur instead. Sorry. I meant to use sulfur instead. Let's put sulfur there. So how many, so sulfur has how many valence electrons?
6.
6, right? So there's 2 more. So there's a total of 26 electrons. So we'll put them around the outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 24. There's 2 left over. We know when there's electrons left over, they go in the middle. So according to Axe body spray, what is that? What is our AXE going to be for that molecule? So sulfur is our central. How many, what's X? What's the value of X?
4.
4 bonding regions. And how many lone pairs for the sulfur?
1.
1.
It'd be a seesaw shape.
So, right, it would be, so it would not be pyramidal. If that was silicon, basically it would look exactly the same as the tetroiodomethane, because silicon is the same number of valence electrons as carbon does. And so the molecule would have the same shape. This, on the other hand, has a slightly different shape because it is not completely symmetrical. So it has a seesaw shape. So basically that means it is going to be nonpolar or polar.
Polar.
That's going to be a polar molecule, right? Because we have 4 bond dipoles pointing toward the fluorines, but they are not symmetrically arranged because we have this lone pair sort of screwing up the shape. So that means that those 4 bond dipoles are not going to be all pointing in exactly opposite directions. They're going to be pointing slightly in the same direction, giving the overall molecule a molecular dipole. So what would be the strongest intermolecular force for that molecule?
Would this be dipole-dipole?
That would be dipole-dipole, right? Because you have a molecular dipole now pointing towards the fluorines. So this one would be dipole-dipole.
And I was just wondering for D, in order to draw the Lewis structure, would it just be the aluminum, because aluminum has 3 valence electrons. So
No,
would it just-
aluminum does not have 3 valence electrons. That's aluminum ion, remember.
Oh,
So if you were drawing the Lewis structure of it, you would put
because I
8
thought,
valence electrons around all the chloride ions, and you'd have none on there'd be none on the aluminum ion.
oh
because
yeah,
it's
yeah,
given
that's
them
what I
all
was
away.
thinking. I thought it was 3 valence electrons because it was in the third row.
No, aluminum atoms have 3 valence electrons, but that's not aluminum atom, is it?
Oh, I see.
Yeah, it's aluminum ion. So if you have like a piece of aluminum foil, all the aluminum atoms in the aluminum foil have 3 valence electrons. They do. But when you have an aluminum ion, it's given all 3 of those electrons away. So now it doesn't have any. Or you could say it has 8, either way. So you've emptied one shell and now you move down to the next one. But it'd just be easier just to give it none.
Would you be able to draw it, please? I just
Would
want to
just-
make sure I.
It would just look like this. You just would take the,
Oh,
yeah, so no valence electrons on it and then 8 on the chloride ions. But generally we don't really draw Lewis structures of ionic compounds because there's really no point.
oh, okay.
Because really, one of the reasons to draw Lewis structures of non-ionic compounds is to figure out whether they're polar or not. Ionic compounds are all super polar, so it doesn't, it's really, it's you don't have to bother. So who has the strongest intermolecular force of those 5?
Aluminum chloride.
Yeah, it's the only ionic one. So since that is ionic, that is going to have the highest boiling point. Who's going to have the lowest? We've got 3 molecules. No, we have 2 molecules that are non-polar.
Would it be the neon?
Carbon tetraiodomethane is nonpolar, and neon is nonpolar. Ozone's very, very, very polar, and sulfur tetrafluoride is polar as well. So they're going to be in the middle. But we have 2 non-polar molecules. Which one is going to have the lower boiling point?
Wouldn't it be the neon because it's just one element?
It's not because it is neon, but it's not because it's just one element. How do nonpolar molecules increase their London dispersion force?
The longer it is, right? Because tetraiodo, that means that it's longer than the neon.
Basically, it's bigger. The bigger a molecule is, the more electrons it has. And the more electrons it has, the larger you can cause these dispersion forces. Because remember, London dispersion force comes when you have a molecule, let's call it molecule X. Molecule X has a lot of electrons around it. It's much easier to just gently push some of them so that you have a few more on one side than you have on the other side. So you have a very tiny, slightly positive charge on one side and a very tiny, slightly positive negative charge on the other. the more electrons you have, the easier that is to do. Now, if you have another element Y that only has like 6 or 7, 10 electrons or whatever, it's much, much harder to move them from one side to the other. The larger the molecule is, the easier it is. So that's why larger molecules have greater London dispersion force than small molecules. So methane, for instance, is a gas. It's a hydrocarbon, but a much larger hydrocarbon is a solid at room temperature. This would be like something like, really big, like candle wax or something. It's still a hydrocarbon. It's still completely nonpolar, but it's so big that it makes a lot of London dispersion force interactions at the same time. Whereas something small like methane can only make like 1 or 2 and very weak at that. So it's the size. So if you have 2 molecules, both of them are nonpolar, and you don't know which one of them is going to have a higher IMF and therefore a higher boiling point, it's always going to be the bigger one. It's really the one with the more electrons, and that's generally the larger. If it's just an atom, whoever has more electrons is going to win. If it's a molecule, basically the larger the molecule, the more electrons it's going to have. So the one with the most electrons wins. So any questions about that one?
So in like the exam, you would just explain that because the larger the molecule is, it has more London dispersion forces. So that means that neon would be the lowest one.
Yeah.
Okay.
Yeah, neon is the fewest electrons and it's the smallest, therefore it is the lowest IMF and it would boil at the lowest temperature. In fact, I think tetraiodomethane might even be a liquid. I'm not sure. I think it might be because iodine is big. Iodine is a big atom. So I think that may have enough London dispersion force to make it a liquid at room temperature, but I'll have to double check on that. Because even if because I know that, oh my God. This is irritating. Okay, is everyone back?
We're here.
Man, that is so irritating. So it did it again. What the hell? What's going on? So something like carbon tetrafluoride is a gas. And then the larger each of those halogens gets, the more the IMF and the more higher the boiling point. Carbon tetrachloride, that's actually a liquid at room temperature, but has a fairly low boiling point. And then, yeah, carbon tetrabromide would be even bigger. That's a liquid. Yes, yeah, so carbon tetraiodo or tetraiodomethane definitely is a liquid at room temperature. Okay. Don't. Okay. All right, number 2. You have a PivNerd question. We're gonna have a couple PivNerd questions here. So I've got a certain volume of argon, and it's going to be cooled from 400 degrees Celsius to 10 degrees Celsius, but the pressure doesn't change. So basically, if I had a balloon at 400 degrees C filled with argon, big balloon, and I cooled it down to 10, what would be the volume, the new volume of the balloon? So how are we going to deal with this particular question?
Good old Pivner.
Good old Pivner. Yeah, so I really believe in just sort of just for every gas law question, I just write that down regardless of what it is. Because I think it's what's really confusing, I think, for students and for myself. I have trouble remembering what's the relationship between pressure and temperature and volume and everything. You know, do I divide? Do I multiply? What do I do? But if I just have Pivner in front of me, I can just derive it on the spot and figure it out. I'll show you what I mean. So what are we trying to solve for here? Which one of these P, V, N, R, T, which one are we trying to solve for?
Volume.
Trying to solve for volume, right? And what is being changed?
Temperature.
The temperature is being changed, right? So the temperature is being changed. The pressure is staying the same. So what I would do at this point is then try and put volume and get volume and temperature by themselves, and then have everything else on the other side. So let's do that. So I want to, so basically V is then going to equal nRT divided by P. So what I want is T to be with V. So I'll divide both sides by T equals nRP, right? Does that look right to everybody? You see what I did there, or should I do that again?
Can you do it again?
Sure, no problem. So I got my old Pivner here, and we're solving for volume. We're solving for V. So I'm going to put V by itself. So I'll divide both sides by P. And that gives me volume equals nRT divided by P. But T is going to be changing. I want to put V and T on the same side of the equation. So what I will do, oh, Seuss, man. So I'm going to divide both sides by T. Divide that by T. So that gets rid of T. And now I have V over T equals nRP. Does everyone see how I did that now?
Yep.
Okay. So the advantage of doing that is that now I have the relationship between volume and temperature. And I can see that N, is N changing? What does N stand for?
Moles.
Moles. So is the number of moles changing?
No.
No.
No. And R is a constant. That's not going to change. And is P changing? Is the pressure changing?
Constant.
No, it's constant too. So none of these things are changing. So what that tells me is that any volume divided by temperature is going to be constant. So that means my initial temperature divided by the initial volume divided by the initial temperature is always going to equal the final volume divided by the final, that's wrong, divided by the final temperature. That is the relationship between volume and temperature. As temperature goes up, volume goes up too. As temperature goes down, volume goes down. Because when you divide one by the other, you always get the same thing, provided everything else is constant. And so now we have a relationship we can use to solve the problem. Now all I need to do is plug in my initial volume, the initial temperature, and the final temperature, and I could solve for the final volume. Does that seem pretty straightforward? Yes, no? Am I going too quickly? We can only do this if everything else is constant. So number of moles is constant, the pressure is constant, and R is a constant. We can't do this if the pressure changes, or we make or we make new gas, or we lose some gas. We can't do this then. But if the pressure is the same and the moles are the same and R is always the same, then we can do this fairly simple relationship. So I have volume 1 divided by temperature 1 equals volume final divided by temperature final. Everyone's kind of quiet. So does that not make sense? I mean, this is one of the gas laws, but we have I think it's Boyle's law. But I think rather than trying to memorize that, I just find it easier just to get it from Pivnert, because Pivnert it's really easy to remember. I can't remember all the different laws.
But on the final, we still get to use the reference sheet, right? You know, the one that you provided.
Yeah, I don't think the reference sheet has all the different gas laws on it. I think it just has Pivnert.
Oh, actually, it has PV V1 equal divided by T1 equals P2 V2
Oh, okay.
over T2.
That's fine. Yeah, but just you still need to know when you can use that and when you can't. You can only use that at constant pressure and constant moles. You can't use it any other time. So that's why I just derive it to make sure. All right, so let's plug in our numbers. So what's our initial volume?
And 24 ml.
Sorry?
124. I'm sorry, 45.09
Right,
liters.
liters, right. So we have 45.09 liters. And what's our initial temperature?
Sorry to interrupt. I just want to make sure, because it said constant pressure, that's the reason why you can disregard the P in the equation, right?
Oh, we don't disregard it. It's just going to be constant.
I mean, you didn't put it in the equation. That's what I meant by like disregard it.
No, we don't know what it is, but it doesn't matter because it's constant.
Oh, okay.
Because V1 T1 it's equal to NR divided by P. So it means my initial volume and my initial temperature are going to be equal to this. And that's, I don't know what the number is, but I also know that my final volume divided by my final temperature is also going to be equal to this. Therefore, they're equal to each other. That's the relationship I'm taking advantage of. I don't know what they're equal to. I just know they're equal to each other because this is a constant number. That doesn't change. So I'm not ignoring the pressure. I'm actually taking advantage of the fact that it's a constant. So what's my initial temperature?
$400.
So I just put in 400 Celsius?
No, you have to
Converted to
put,
Kelvin.
It's got to be Kelvin. That's right. So what's that temperature going to be in Kelvin?
673.15 Kelvin.
So you got that by taking 400 C, and what did you add to it?
273.15.
That's right. That's the conversion. So it's 673.15 K. And that's going to be equal to our final volume. And that's actually what we're trying to figure out. So we don't know what that is. Divided by the final temperature. What's the final temperature?
283.15 Kelvin.
Right. So now we just solve for the final volume. So what's the final volume going to be?
If you want to get rid of the, if you want to figure it out, would you just multiply the 283.15 to both sides? Is that how you would separate the VF from the temperature?
So you'd multiply these two together and then
Oh.
divide by that. Oop. So what do we get for our?
I got a 18.966401 liters.
18.9664. That's right. So how many significant digits should we put in our answer? Four. But why not one? Because 10 degrees.
But didn't you have to convert that to Kelvin?
We did. Yeah, so actually the temperatures both have 5 significant digits in them. And the liters is 4. So right, we would take 1, 2, 3, 4. So what's our final answer?
$18.97 liters.
That's right. 18.97 liters. So then any of these sort of questions, have a look at your final answer and see if it makes any sense. So very, very quickly, your temperature is pretty much gone down by a little more than a factor of 2. So your volume should have gone down by a little more than a factor of 2. And then when you look at it, was 45 and now it's 19. So it's gone down by a little more than a factor of 2. So that sounds right. So you should be fairly confident that you must have put this together properly. Because if you got an answer that was like, 4 times less, or if you got an answer where the volume went up, then something's screwy. So you could always just do a quick check. So the ratio of these two should also be the ratio of these two. I mean, that's how the math works, right? So if your temperature goes down by a factor of 2, your volume should go down by a factor of 2 as well. And here it looks like it did. So we probably did that one right. Oh boy. So we take our all-time favorite thing, which is stoichiometry, and then our second favorite thing, which is Pivnert. And we're going to use both of them. So here we got a stoichiometry problem. So what is the very first thing we do when we have a stoichiometry problem?
Balance the equation.
Yeah, we do. So have a look at that. Is that a balanced equation?
No. Oh, wait. I need to double check.
So is that balanced or
Yes.
it is actually. So this one's a little tricky because you look at it and you see 4 chlorines. Oops. You see 4 chlorines on this side and you see 2 chlorines on that side and you go, oh, there's something wrong. And then, yeah, so that's a really common mistake is people will forget that there's 2 chlorines actually, or chloride ions with the manganese there. So there actually is 4 chlorine atoms on both sides. So that actually is balanced. So we can start. So where do we start with this? What's the product we're looking for?
Volume.
Chlorine gas. So which one is that?
The CO2.
Right, so we're looking for this. So that's our product. We're going to try and figure out the volume of chlorine gas. That's what our final answer should be. Now, what's the reactant we're given to work with?
Hydrochloric acid.
Yeah, so it's the HCl. So that is our reactant. And so we have to assume that there's a excess. And what do we call that? What would this be called? Is that ionic or covalent?
Is that ionic? Because it's a transitional metal, I believe.
It's a metal, right? That's manganese is a metal. So yes. So what will we call that?
Manganese oxide?
Nope.
Oh, you have to have the Roman numeral, don't you?
That's right, because it's a
Transitional.
transition metal.
Is that manganese 4?
That's right. So that
Oxide?
would be manganese 4 oxide. What would we call this?
Manganese 2 chloride.
Manganese 2, very good. Notice the difference. This is what we call an oxidation reduction reaction. We didn't really get into this, but notice that the charge on the manganese went from +4 to +2. That means it gained electrons from somebody. And it gained those electrons from chlorine, actually, because the chlorine went from a charge of -1 over here to 0 over here. So chlorine ion gave its electrons to manganese. So one got oxidized, the chloride ion got oxidized, and the manganese metal got reduced. So that is the reactant that we have, is the HCl. So how are we going to figure out how many moles of HCl we have? Because that's what we need, right? We need to, in any stoichiometry problem, we need to know how many moles of reactant we have so we can calculate how many moles of product we're going to get. So how many moles of reactant do we have?
Why don't you do the convert the milliliters to liters to moles, and then the relationship of the moles of hydrochloric acid to the relationship of chlorine gas based off of the balance equation.
There you go. So how many liters of HCl do we have?
124.0 milliliters.
We need to convert that to liters. So how do we convert it to liters?
1 liter equals 1,000 milliliters.
Okay. Now we need to convert liters to moles. How do we do that?
We use the molarity. 0.750 moles over liter.
So that gets rid of our liters and we're left with moles. So how many moles of HCl do we have?
Point 0.093.
Remember, I get cranky when I see a 0.093, 0.093. And the reason for that, it's really easy to make a mistake when you have just a decimal there. It can easily, it can be mistaken for something else. So always have a decimal there. So that's how many moles of HCl we have. So what's our next step?
Is it see the relationship between the moles of hydrochloric acid to the moles of chlorine gas?
Right, we need to take our moles of HCl and convert them into moles of chlorine. So how do I do that?
You look at the relationship.
What do I put on top? And what do I put on the bottom?
1 mole of chlorine gas to 4 moles of hydrochloric acid.
Right. And then, so how many moles is that going to be?
Zero 0.02325 moles
Yeah.
of chlorine gas.
2,325 moles chlorine gas. So now that I have that's the amount of product we would make. And normally we'd be done at this point because normally our stoichiometry equation is like how many moles. Maybe we convert it to grams. But in this instance, this is a gas. And so we very rarely measure gas in terms of grams. We don't really say we have like so many grams of CO2 or grams or whatever. We normally, when we talk about gas, we talk about how much volume and pressure, because we have it in a container. It makes it a very heavy container, which makes it difficult to measure the mass of the stuff inside. But what we can do is we know what the volume of the container is, and we can easily measure the pressure inside. So that's why we really don't measure gas in terms of mass. It's always pressure and volume. So what do we do with this information to give us the final answer? Because our final answer is volume. How many liters of chlorine gas? So what am I going to do with this to turn it into a volume?
We will use the PivNet.
We're going to use our friend that we've missed for so long. It's been weeks since we've done any PivNet. Right. So what am I going to do with PivNet in order to solve for volume?
Divide P to both sides.
Yes. So now V is going to be equal to N. And what's N again?
Would it be what we calculated, what the moles were of
Moles,
chlorine?
right. N is the number of moles. R is a constant. T is the temperature, and we know what that is. And P is the pressure. We know what that is. So basically, we have all the information we need to solve for the volume. Now we just need to plug those numbers in. We're good to go. So V is going to be equal to our number of moles, 0.02325 moles, times R. And what are we going to use for R?
The constant,
What's the value of R?
0.0822. 8.206 liters times atmosphere over Kelvin over mole.
82, was it 006? Is that what you're using, or 821?
06.
Yeah, okay. Liter atmosphere, mole kelvins. I just love the units for that. Times the temperature. What's our temperature going to be?
Three hundred 63.15 Kelvin.
Right, so we have to add our 273.15 to 90. So that is, what was it again? Sorry?
363.15 Kelvin.
Yeah. And then we just divide that whole thing by the pressure. So do we need to do anything to the atmospheres? Do we need to convert that?
No,
No,
How come?
we're given it at, because the atmospheres cancel out.
Because it's part of this value of R. There's lots and lots of different values of R depending on how you're measuring the pressure. There's values of R where you're using atmospheres. There's values of R where you're using torr. There's values of R where you're using millimeters of mercury. There's all different values of R. But we're going to use the one for atmospheres because it's the easiest one. I can picture atmospheres in my head. So, and that's the unit we have. That's why it's important to always have the units around to make sure that you're doing things properly. So now we have atmospheres on the top and atmospheres on the bottom, so we can cancel those. I have moles on top and bottom, can cancel those. And I've got Kelvin on top and bottom, I can cancel those. So the only unit I have left is liters, and that's what I want. So now it's just a straightforward calculation. So how many liters do I wind up with?
I got a 0.749029
What?
liters.
Liters, right. Always have the unit. Okay, so how many significant digits should we use?
Should be 3
How come?
or 2 because of the molarity. Oh no, just sorry, 3.
3.
Yes,
So how many do we have there? How many significant digits in the molarity?
3.
3, that's right. That 0 is significant because it's past the decimal point. There's a reason for it to be there when it's past the decimal point, because we don't use it for the calculation. So it's there to show you that it's significant. How many there for the volume of HCl?
4.
There's 4. And then what about the atmospheres?
3 as well.
3. And the temperature is always tricky because sometimes we forget that we're going to be adding that to 273.15. So that actually has 5 significant digits because we're adding them. So, so we should have 3 is our lowest, right? So we should have 1, 2, 3. So our final answer would be 0.749 liters. So again, since this is a gas problem, if you want to check your work, what you can do is take the number of moles and multiply it. How many at 1 atmosphere of pressure and it's 0 degrees, what should a volume should a mole of gas take up? Maybe you don't remember this. So remember at STP for gases, standard temperature and pressure, the standard temperature is 0 degrees C and standard pressure is 1 atmosphere. And at those conditions, 1 mole of gas takes up about 22.4 liters. So what you can do is take the number of moles you have and just multiply it by 22.4 liters. And I think in this instance, you get somewhere around like 0.55 or something. So you look at that and you say, well, that's less than what I'm seeing. But remember that the temperature is higher and the atmospheric pressure is lower. So both of those should give you a larger volume. So you're in the ballpark. That looks to be about right. So it also lets you know that you're probably pretty close to the right answer. So it's also, that's another little trick you can do just to be sure whether you've done the problem correctly with gases. Okay. Oh, any questions about that one? Let me put the stuff back out there before we move on. We'll do one more, then we'll have a little break.
Sorry, can you go over how did you double check the work again?
So it's standard temperature and pressure, and that is, oops. It's standard temperature and pressure. That's 0 degrees C and 1 atmosphere pressure. 1 mole of gas takes up around 22 liters of space. That's the volume. So if you've calculated moles of gas and you want to do a quick and dirty calculation to figure out what the volume should be, just multiply it by 22. And in this instance, if we multiply it by 22, we get somewhere a little more than half a liter. So remember that half a liter number is at 0 degrees, and this number is at 90 degrees. So at 90 degrees, the volume should be larger. So that looks good. And the atmospheric pressure is also lower. This number is at 1 atmosphere, and this number is at 0.925 atmospheres. So that increases the volume again. So you're in the right ballpark, around 0.5 to around 0.75. That seems reasonable. So you can be fairly certain that that's probably about right. If you had a number that was way different, like, 4 times or 5 times bigger or 4 or 5 times smaller, then you've probably, made a mistake somewhere. But if it's pretty close, then you're probably right. So that's what I meant by that. All right. So let's do this one and then take a break. So, another stoichiometry question. So we're dealing with solution chemistry. And so what is the reaction here?
Is this a substitution? Double substitution?
Oh, sorry. Right. Not yet. Well, yeah, very good. Yeah, I just I just wanted to know what the reactants were and what the product is. But yes, that is a substitution. Leading to a precipitate. That's right. So what are our 2 reactants and what's our product?
Hydrochloric acid.
So we have hydrochloric acid. What's our other reactant? What's that called?
Lead nitrate.
Lead nitrate, right. That is would that be the only name of it? Is lead a transition metal?
Basic metal. It's a basic metal.
Lead is a transition metal. So we have to say what the charge is. So what would the charge on lead be in this compound?
Lead 2.
Right, lead 2. Nitrate has a charge of -1. So these two are, what does this mean? AQ.
Aqueous solution.
Right, it means they're aqueous solution. But what does that mean? If something's an aqueous solution, what kind of compounds are these? HCl and lead nitrate.
Does it just mean it has water?
Means it's dissolved in water, but it means something special in this particular case. What kind of compounds are these?
Ionic.
They're ionic, right? They're both ionic. HCl we think of as being non-ionic because it's, it's got hydrogen and chlorine, but it's a strong acid. And what does a strong acid mean? What does that mean to be a strong acid?
Completely dissociates in water.
Right. So instead of, I don't really have HCl aqueous, what does that actually mean?
Is that hydrogen ions and chlorine ions?
That's right. That means I have H plus and Cl minus. And what does that mean for the lead nitrate?
Oh, they completely dissociate as well.
That's right, because if it's an ionic compound and we say AQ, that means that that ionic compound is completely dissociated. So that means I have +2, sorry. Yeah, that means it's completely dissociated. So what's my product going to be?
Lead 2 chloride and nitric acid.
So we don't put AQ for that. There's an S there. So what does that mean?
Solid.
So what is that? So because it's a solid,
It's
what happened to it?
It precipitated.
It precipitated, right? So that means it's no longer an aqueous solution. It's now a solid. And you're right, the other product is nitric acid.
Oh, never mind.
And that's going to, and nitric acid is also a strong acid. So that means H plus and NO minus. Basically, nothing happens to the protons, nothing happens to the nitrate ions. So what do we call those? Anyone remember what we call those in a reaction like this? They don't really do anything. They were there at the beginning and they're there at the end.
Is it a spectator?
A spectator ion, that's right. They're not involved in the reaction at all. Basically, the only purpose of the H plus is to supply chloride ions. Because the only things reacting are the chloride ions and the lead. ions. So that's our reaction. So what do we need to do next? If that's our reaction?
You don't need to draw the NHNO3 minus.
Yeah, we can put that in there.
The good old balanced equation.
You're gonna balance it, right? So is it balanced right now?
No,
No. So what do we need to do to balance it?
is it 2 hydrochloric acid, 2 lead? I can't say it. NO3, 2
Nitrate, lead nitrate.
lead nitrate,
So
and then 2.
why do we need to change the number of lead nitrates? I have one atom of lead on the left, I have one atom of lead on the right.
It's in because it says NO3 and then it says 2.
So where are
it
we
has
gonna
to be
put, where are we
balanced.
gonna put 2 to balance the
Oh, on the
nitrate?
product side. Right,
Where we put it?
the product side,
Yes. On which one?
HNO3.
Right. So that's our balanced equation,
And how do you know that HNO3 would be aqueous?
because that's a strong acid.
Oh, okay.
Yeah, it doesn't form precipitate. If it formed a precipitate, it would say so. But it doesn't. Yeah, it's a strong acid. So basically it's hydrogen, protons are very, very soluble. Nitrate ions are very, very soluble.
And
So-
wouldn't it also be 2 by the reactant side where the lead is?
No, why? We have one atom of lead on both sides.
Oh, okay.
Lead's
I was
balanced.
misreading it.
Yeah, so chloride's balanced, hydrogen's balanced, lead's balanced, nitrate's balanced, everything's balanced. So remember, you balance the nitrate ion. You don't balance the nitrogens and the oxygens separately. You'll go crazy doing that because they stay together. They don't break up. So it's going to be nitrate ions on one side and it's going to be nitrate ions on the other side. So now we have a balanced reaction. So what's our next step?
Pivner, right?
Are we making any gases?
Oh. No.
No, this is all in solution. So we're not making a gas. Our product isn't a gas. Our product is a solid. So if we were making like Cl2 or something, that would be a gas, but we're not doing that. Or if we were making hydrogen gas, but we're not doing that either. So where do we go from here?
Determine the moles of hydrochloric.
That's right, because we're given the number of moles of this. So we're told how many moles of lead nitrate we have. And the question is, how many moles of HCl will we need to react completely? And we're not even asked like to figure out how much product. So really all we need to figure out is what's the relationship between the two reactants. So how are we going to do that?
Use the mole ratio.
Use the mole ratio. So what do I write down first?
0.290 moles of lead nitrate.
Right. I'm just going to put lead there because it's it's just easier. So what's my next step?
Multiply 2 moles of hydrochloric on top and 1 mole of the lead at the bottom.
Right, because that is the relationship 2 to 1. And remember, if there's 1, we don't put the 1 in there. That's just understood. So what's next? So that would tell me the number of moles of HCl, but that's not the question, is it?
No, look for the volume.
I want a volume, right? So how am I going to wind up with a volume at the end? What's my next conversion?
Use the molarity, right?
So how am I going to use the molarity?
0.750 moles, and then the top would be 1 liter of hydrochloric acid.
Right, so 1 liter and 0.75 moles HCl on the bottom. So that gives my moles of lead are gone, my moles of HCl are gone, and I'm left with liters. That's what I want. So what's my final answer?
I got a 0.773333 Liter.
That's a lot of threes.
liters.
Liters, right. You always want to look for the unit. So how many significant digits do we have?
There should be 3
Why is that?
from the molarity and the moles.
So we got 3 significant digits in the molarity, because that's a 0 behind the decimal point. So there's 3. And how many in the number of moles?
3 as well.
3 as well, right. So each of those trailing zeros is significant because it's past the decimal place. So what's our, so 1, 2, 3. What's our final answer?
0.773 liters.
Yes, excellent. Yeah,
So,
so it
um,
says liters. If it said volume, you could put down 0.773 liters, or you could give 773 milliliters. Either one of those would be correct. But it says, actually says liters here. So this is the answer we're looking for.
so like Pivner, that's specific to like gas.
Gas only.
Okay.
Yep.
And so like for the question previously, it just said how many, oh, okay, if it didn't say how many liters, if it just asked for volume, then we could give it in liters or milliliters. But because that question specifically asked how many liters, the answer has to be in liters, correct?
Right.
Okay.
And generally, our gas questions, since the value of R is in liters, we're going to get the answer in liters. But if it's a really small number, you could give it in milliliters, or you can convert it to gallons if you want. But yeah, generally we use liters as the standard for gas. All right, let's take a little 5-minute break. I'm going to tuck some people in, and then I'll be right back. Okay. Hopefully we're still recording at this point. Oh, yep. All right. So here we have an acid base question. So what do we do when we have an acid base question? I mean, we can see what kind of reaction it is. It is a neutralization reaction. So when we have a neutralization reaction, what are our products?
Isn't it a water and a salt?
Water and a salt, right. So which one is our acid and which one is our base?
And AOH is a base, strong base.
So that's our base. And what's our acid?
H3PO4.
And what is that?
Phosphoric acid.
Phosphoric acid.
And I
Right.
believe that's also a strong acid, right?
It is not.
Oh, it isn't.
That's
Which
a
one
weak.
was the strong acid? That it looks similar to that.
Sulfuric acid. It's
Oh, okay.
H2SO4. That's a strong acid. Yeah, that looks very much like it. Yeah, this is actually H3PO4. Phosphoric acid is actually in Coca-Cola. It's one of the things that gives it a particular Coca-Cola taste. So what are our products going to be? What's our salt?
Sodium phosphate?
Sodium phosphate. What's the formula for sodium phosphate? Is that it? NaPO4?
Na3PO4.
That's right. Phosphate is a -3 charge. And our other product is water. So what do we do next?
Just wondering, in this kind of problem, will we have to write the water as a product? Or would water be kind of like in the previous product being like a spectator ion kind of thing? Well, it's not an
Is
ion,
it?
but
No, the hydrogen is not a spectator ion in this one.
okay, so you would have to write the water. Okay.
Yeah.
Oh, you
Yeah,
would
because the
balance
hydrogen goes from one place to another. It is not a spectator in this reaction. The spectators in this reaction, what are the that's a good question. What are the spectators in this reaction? That's a really good question. I have to write that one down for the final. What is it? So who are our spectator ions in this reaction?
is that like a trait question? Like there's none?
No.
Oh.
Well, actually, in this particular reaction, that's true. There aren't any. Because there's a weak acid. If there was a strong base and a strong acid, then there would be. If this was HCl and it formed NaCl in water, then sodium and the chloride ions would be spectator ions because they'd be there at the beginning and they'd be there at the end and they'd have the same charge. But in this instance, they're not, because the sodium goes from being associated, being positively charged and associated with OH minus to being associated with phosphate. And it's closely associated with phosphate. It's basically stuck to the phosphate. It's still positive, but it's fairly associated with the phosphate. So you could say that the sodium and the phosphate ions are spectators, but I'm going to save that for another problem. All right, so what's the next step we do with this particular equation?
Balancing the equation.
Right, we need to balance it. So how are we going to do that?
Place 3 in front of the sodium hydroxide.
Right, we need 3 sodiums, because there's 3 sodiums on the right. What else?
Then another 3 for the hydrogen. That's the water in front of water.
Right, because we have 6, now we have 6 hydrogens. We have 3 there, and we have 3 there. So we have 6 on the left, so we need to have 6 on the right. So it makes 3 waters. And is that everything else balanced?
Yes.
Yes, I think so. Okay. So we have a balanced equation, we can get started. So where do we start now? Because we're being asked, what's the concentration of the acid? So which one is the acid?
Phosphoric acid.
Right, so this is our acid. So we're being asked, what's the molarity of the phosphoric acid? That's the problem. So where do we start? So to figure out molarity of the phosphoric acid, we need 2 bits of information. 2 bits of information. We need to know the moles of the phosphoric acid, and we need to know the volume. Well, we know the volume. There's the volume. So we have the volume. So all we need to know are the moles. So how are we going to determine that?
Milliliter to meter to liter to moles.
How are we going to get? How do we do that?
Is it that when you use the molarity of the sodium hydroxide to try to figure out the molarity of phosphoric acid?
Okay, so what is there a formula or something?
110.0 milliliters, convert that to liters, convert that to moles, and then from the mole ratio, figure out the moles of phosphoric acid.
Right. All right. So we need to figure out the number of moles of sodium hydroxide first. So here's our volume. So what's my first conversion?
One liter at the top.
Right. I want liters. I don't want milliliters. So what do I put on the bottom?
1,000.
1,000 milliliters. Okay. And then where do I go from there? So now I have liters of sodium hydroxide. What next?
0.105 moles sodium hydroxide over 1 liter of sodium hydroxide.
Okay, that gets rid of my liters. Now I have moles of sodium hydroxide. What do I do next?
Mole ratio.
Okay, so what do I want to put on top?
Moles of phosphoric over moles of sodium hydroxide.
What's my ratio?
So it's going to be 1:3.
1 to 3. Okay. So now I've got moles of phosphoric acid, but that's not the question, is it? What am I being asked for?
Molarity.
I'm being asked for molarity, right? So you can either just calculate moles of phosphoric acid at this point, and then divide by the volume, or you can just do another conversion. What would the last conversion be?
1,000 milliliters over a liter.
We need to use the 125.0 ml.
Oh, I see what you mean. Right, so actually I want liters on the bottom, right?
Yes.
Because I want to have moles over liters. And then 1 over 125 mils. This out of the way. Man, that is a lot of conversion. So I got moles. My mils cancel out and I have moles over liters. So man, after all that, what do I come up with? See if I get the same answer.
Zero point 0.0308 molarity.
Right, that's what I got too. So if you want to do, way to do a quick check of this one is since the volumes are fairly similar, right? So I've got about 125 mils of acid, I got about 110 mils of base. That's almost the same volume. If the concentration of the base is 0.1, and I need 3 times more of it than acid, or on the other hand, I could look at it, if the concentration of the acid is about 1/3 of the base, because it's got 3 protons, so I only need 1/3 as much. My concentration should be about 1/3 of 0.105. And when you look at it, it is. It's around 1/3 of 0.1. So that's probably the right answer. Yeah, so the tricky part of this one is you have to remember the mole ratio. Generally, the titrations we do with a strong acid and a weak, or a strong base and a weak acid, like acetic acid or something. Generally, we're just titrating 1 hydroxide ion to 1 proton, but phosphoric acid has 3. So we need to make sure we do that. The other way to do that is, let me go back. Probably remember concentration acid, volume acid equals concentration base, volume base. That sound familiar? You
Yep.
can do that if there's a single proton on the acid and a single hydroxide on the base. But in this instance, there's 3 protons on the acid. So you need, so that would only be 1/3. That would give you the same number of protons on one side, and the same number of hydroxide ions on the other. So that'd be a quick and dirty way of doing that. But it's tricky because a lot of people make the mistake, they'll put either 1/3 or 3 times on the wrong side and screw it up. So if you're not sure how to do that, then I would just go through the long process that we did there. Okay. This should look kind of familiar because it is evil. All right, so we have a mass. We have a diprotic acid. What does that mean? A diprotic
Two hydrogens.
Right, it means, just means it has two hydrogens. And so we can just use, we usually use like H2X for that. We don't know what X is, but we know that it's got two protons. And we have a mass, and we have a molar mass. And it's titrated with a strong base. So what's our reaction going to be? So we know what our acid is. It's H2X. What's our base?
Sodium hydroxide.
Sodium hydroxide, right. So it's H2X plus sodium hydroxide. And since this is a titration, we're doing a neutralization reaction. So what are our products going to be?
Water and salt.
Water and salt. So water, what's our salt going to be?
Na2X.
That's right. Excellent job. Yeah, we don't know what X is, but we know it has a charge of -2. How do we know that? Well, because it has two hydrogens associated with it. So we know that sodium always has a charge of +1 when it's an ion. So if X has a charge of -2 and sodium has a charge of +1, it's going to take two sodiums to balance the charge on X. Really good job. So is this a balanced equation?
No, because sodium on the product side is 2.
Right, it's two products, two sodium ions on the product side, and only one on the reactant side. So how do I fix that?
You need to place 2 in front of the sodium hydroxide
Yeah,
and then
Oops.
2 in front of water.
so we need 2 moles, because it's diprotic, it means it has 2 protons. That means I'm going to need twice as much base. I need 2 moles of base for every 1 mole of this acid. So the last one we did was actually a triprotic acid. It was phosphoric acid, had 3 protons. So we call that a triprotic acid. So, right, so we need to have 2 moles of sodium hydroxide, and that's also going to give us 2 moles of water. So now it's balanced. So where do we go from here? Oops, got the wrong page up. There we go. So what's our next move? Since this is a stoichiometry problem, what are we going to need to figure out first?
Number of moles.
We're going to need to figure out a number of moles of something, right? And so we don't know, we're being asked what's the volume of sodium hydroxide required. So basically the number of moles of sodium hydroxide is unknown at this point. So if the number of moles of sodium hydroxide is unknown, how do we determine it?
We can compute for the moles of the diprotic acid.
Right. Excuse me. Yeah, we don't know the number of moles of base, but we can calculate the number of moles of acid. So let's do that. So we've got 565.8 milligrams of H2X. Now I want to convert that. What's my first conversion going to be?
So convert it to grams first.
Yeah, let's convert it to grams. So where do I put grams? On the top or the bottom?
At the top.
On the top, definitely. Milligrams on the bottom. So how many milligrams to a gram?
1,000 milligrams.
1,000, right. So that gets rid of my milligrams. Now I've got grams. But I don't want grams, I want moles. So how am I going to get moles out of this?
Use the molar mass.
And we know what the molar mass is. What do I put on top?
Moles at the top.
I want moles, right? That's what I want. So I always put what I want on the top and what I want to get rid of on the bottom. So how many grams per mole is our H2X?
225.6 grams per mole.
225.6, that's right. So that gets rid of my grams. So now I've got moles of H2X, and that is what I want. So how many moles is that?
I got a 0.00250.
250?
250, yes, 79.
79, okay. Moles H2X. All right, so so that's how many moles of H2X we have. So what do we do with that information to get to volume of sodium hydroxide? So I've got 0.002579 H2X. How do I go from that to volume of sodium hydroxide?
I got 252. Not 250. So I got 0.00252. I don't really know if it makes much of a difference, but
Yeah, I don't have my calculator with me. Someone else want to double check?
I got the same as what Ava got.
So 25079.
Yes.
All right, let's go with that. So how do I convert that to a volume of sodium hydroxide? What's the next conversion I want to do? So I have moles of H2X. What do I do with that?
So we're going to use the molar ratio.
Yeah, I don't want moles of acid. I want moles of base. So what do I put on the top?
The base. Moles of base. I mean, ratio.
Okay. So what do I put on top? The base or
Two.
the acid?
Oh, the base.
The base. I want my sodium hydroxide. So there's 2 moles of sodium hydroxide for every 1 of H2X. So that gets rid of my moles of H2X. Now I have moles of sodium hydroxide. So what do I do with that to get me a volume?
Use the molar concentration.
That's right. And remember, I want to get an answer in a volume. So I want liters at the end. So what do I put on the top? What do I put on the bottom?
1 liter for every 0.0755 moles. of
That's right.
sodium hydroxide.
That gets rid of my moles of sodium hydroxide, and I'm left with liters. That's what I want. So I think we're there. We think we're pretty much there. So how many liters is that?
I got 0.0664.
0.0664 what?
0.66436 liters.
Liters, right? That's what I was getting at. So how many significant digits should we use?
Three
Three, right? Why three?
from the molarity of sodium hydroxide.
That's very good. Yeah, so there's 4 in our mass of diprotic acid, and there's 4 in the molar mass. So we would have figured out the number of moles of acid to 4 significant digits. Notice we did not round that number to 4. Don't ever do that. Don't round. I don't know how I must have said this at least a couple dozen times by now. But yeah, do not round your numbers until you get to the very end, because you're going to be throwing away precision. So we kept 5 significant digits, even though there isn't 5, there's only 4, but we kept 5 digits of moles of acid. And we went all the way through, but we're limited by the 3 significant digits in the concentration. So now we have to limit ourselves to 3 significant digits for the volume. So what would our final answer be?
0.0664 liters.
0.0664?
Yes.
Yes, that's right. And if you wanted to give that in milliliters, what would it be?
$66.4.
That's right, because we moved the decimal 3 places for 10, 100, 1,000. So 10, 100, 1,000, 66.4 milliliters. Now, what about the second part of the question? What if I dissolve that amount of acid in 100 mils of water before we started? How would that change the volume of sodium hydroxide required? Would we add 100 mils? Would it be 166.4 mils? Excuse me. Drink of water. So would it change the amount of base required if I dissolve the acid in more or less water before we started? Does that change the amount of base required? What do you think? So if in this experiment, I dissolved that amount of acid in 50 mils of water, and we did the titration, and then we did a second titration with exactly the same amount of acid, but this time dissolved in 100 mils of water, would that change the amount of base we would use to titrate the acid? Yeah, nobody's going to even guess.
I don't think so.
Okay, how come?
What was the same amount of acid?
The same amount of acid in what measure? It's the same number of what?
Concentration?
It isn't the same concentration though.
Mm.
If I dissolved the acid in twice as much water, the acid would have half the concentration, but something else would not change.
The molar mass?
The what?
The molar mass?
Yeah, the molar mass isn't important in this particular example. If I change the concentration, if I dilute something, and that's what I'm be doing here. If I diluted the acid by a factor of 2, I went from like 50 mils to 100 mils. I would change the concentration. The concentration would go down by a factor of 2, but something else wouldn't change. What wouldn't change? What would stay the same? What stays the same when you dilute something? I mean, the molar mass is not going to change regardless of what we do. It's not the molar mass we're interested in. When we're doing a titration, what are we interested in when we're doing a titration? What are we generally calculating? So if I have a certain amount of acid, I dissolve it in 50 mils of water, and then I dilute that to 100 mils. I've changed the volume, I've changed the concentration, but there's something I haven't changed. What haven't I changed?
Number of moles?
The number of moles, exactly. The number of moles has stayed the same. It's just in a larger volume, but the number of moles hasn't changed. So that's why the molarity changes, because we're dividing moles by volume. So the volume can change all over the place, but the number of moles doesn't change. So if I was to dissolve the acid in 10 mils of water, or 20 mils of water, 50 mils or 100 mils of water, the number of moles of acid does not change. So if the number of moles doesn't change, will the volume of the base used to titrate it change? If the number of moles of acid does not change,
No,
will the number of moles of base change too?
no.
No, that's right. So it does not matter what volume I dissolve the acid in. Doesn't matter, because the only thing that matters when you're doing a titration is the number of moles of acid, number of moles of base. That's it. So the volume of the acid doesn't really matter. We try and do it in a fairly small volume, just so when we see the color change, it'll be fairly dramatic. If we make it too dilute, when the color change happens, it'll be so dilute it'll be hard to see. But the volume of base required to do that color change doesn't change. So it's an important thing to remember, because when you're doing a titration, you're calculating moles of acid, moles of base. the concentrations of the acid and base are just a guide to tell you how many moles are there. So that was kind of just kind of a little trick question to get you thinking a little bit about what we're doing.
So, if the acid was dissolved in the 100 milliliters of water, I mean, it just stayed the same then, right? I mean, it would, because it's a weak, well, actually,
No, the amount of the amount of sodium hydroxide that would be required to titrate that acid is exactly the same. It doesn't matter, because that means how many moles of base. Moles of base versus moles of acid is always going to be the same. Always, 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 always. So if I don't change the number of moles of acid, I just change the concentration. I don't change the number of moles. Then the number of moles of base isn't going to change either. It's always going to be the same. So if I don't change the concentration of the base, I'm not going to change the volume either.
so, what would you write as the answer? Would you just say that it wouldn't matter?
And give an
if it was
explanation.
dissolved? Okay,
Yeah, because the number of moles is the same.
okay.
Yeah, that's it. All right, so let's just, well, okay, we can do structural and skeletal. Yeah, why not? We have a little
Sorry,
bit- we have a little
when
bit
you
of
say
time here.
structural and skeletal, you're talking about like, are you talking about, I know what skeletal means, but structural, are you talking about like the Lewis structure?
Basically like the sequence of it. Yeah, the Lewis structure, like, yeah, Lewis structure, basically.
Okay,
Yeah. All right, so let's start with A. What's benzoic acid? Let's just start with that.
So carboxylic acid.
It is a carboxylic acid, that's right. So, but benzoic, what does that mean? What's going to be the
Benzene.
basic part of that?
Benzene.
Benzene, that's right. So let's start with benzene. So there's our benzene. How are we going to get an acid onto benzene? How do we get a carboxylic acid group onto benzene?
You
What does a
attach,
carboxylic group look like?
it's a double bond of oxygen with
Well, remember, we have a
Really?
carbon first, right?
yes. So you draw one bond from the top carbon,
Mhm.
and then there's an OH on the other side.
Right. And then we have like just say it's an R group or something. So how are we going to put this onto the benzene?
The R group is the benzene.
That's right. The R group is the benzene. So we just put, so that's benzoic acid. It's just a carboxylic acid group stuck onto the benzene. But we're not done, right? That's just benzoic acid. We want 2,4-dimethyl benzoic acid. So where are methyl groups going to go?
I was just wondering, does that mean since the benzoic acid is the parent, does that mean that counts as one?
What counts as one?
One
What?
benzoic acid? Like if
No,
you had to count the carbons, right?
that's
The
right.
one that's connected to the acid part, that's carbon 1, right?
That is carbon 1, but we
Okay.
don't have to say it's carbon 1 because that's assumed.
Okay.
So this has a higher priority than methyl groups. So that is just assumed to be the one position. So that is automatically becomes one.
And if so if it was not in a benzene ring, then yes, you would have to label where the benzoic acid is.
Sorry?
If it wasn't in a ring.
Well, if it wasn't in a ring, then it wouldn't be benzoic acid. I don't understand the.
Oh, no,
question.
no, like if this was a problem that didn't involve a benzene ring, then you would have to number where the carboxylic acid is, right? If it was a linear question or problem.
Nope, because it would still be the highest priority.
Oh, because there are times when you do have to number where the parent chain is, so that's.
Yes, if it's
kind
not
of
at the
figure
end,
it out.
if it's somewhere in the middle, then. you
Oh,
do.
okay,
Yeah, but if it's at the end, and carboxylic acids are pretty much always at the end of a linear molecule, right? Because they have a carbon with a single bond, so you can't put it in the middle. So a carboxylic acid is always going to be at the end of a linear molecule. Yeah, so it's always going to be carbon 1. So where do we put our methyl groups?
carbon 2 and 4.
So where's 2 going to be?
You could either put it below the carboxylic acid or above.
Right, it can be at either one. So we can either put it here, or we can put it up there. It doesn't make any difference. So if that's 2, where's 4 going to be?
Across from the benzoic acid.
Directly across. Yeah.
Do we have to write CH3 or is it enough just to draw the line?
If you're doing structural, you put the CH3 in. If you're doing skeletal, you just put the line.
Okay,
Yeah, so the skeletal would just be. So that would, yeah, not much difference. Not much difference. So remember, yeah, with the skeletal, you don't put any hydrogens unless they're attached to oxygen. If they're attached to carbons, you leave them out. But we would put it in here because it's attached to oxygen. So that's it for that one. Oh, right. Yeah, so these two groups, are they ortho, meta, or para from each other?
para.
These are
across.
para, yeah. And what about these two?
Ortho.
Yeah, ortho.
This is just something that one of the tutors told me to remember the differences. So para is across, obviously, but if you're thinking of meta, it's in the middle.
Okay.
So that was kind of, I don't know, that might be a good way to remember.
That's not a bad way to think about it. All right, let's do the next one. So we have 4 isopropyl, 5 propyl octanol. So what's the base? Where do we start?
It's an aldehyde.
It's an aldehyde, right?
So
And how,
it's a double bond with a hydrogen at the end and then the
Mhm.
R group on the other side.
so how big is our R group here?
It's going to be 8.
8, that's right, octanol. So we go 1, 2, 3, 4, 5, 6, 7, 8. And aldehydes are also always going to be at the end because we have to have a single bound carbon. So we can put it at either, so that's an aldehyde group, but we can put it at either end, either a carbon 1 or carbon 8. So that automatically makes it carbon 1. So what are my 2 substituents on this?
Propyl and isopropyl.
Right, so I've got an isopropyl group on carbon 4, and I've got a propyl group on carbon 5. So what's the difference between those two? How many carbons in each one of those?
3.
3, right? They're both 3 carbon chains, but there's a difference between them. What's the difference?
For the iso, it's bonded to the second carbon.
That's right. So we have 3 carbons. If it's an isopropyl, it's bonded to the second one. And if it's a propyl, it's bound to one of the carbons at the end. It's bound to a terminal carbon. Excellent. So which one is carbon 4? Three away from carbon 1, I imagine.
You can't write to left.
So 2, 3, 4, 5. So at 4, what do I put at 4? Is that the one bonded in the middle of the 3 carbons or at the end?
The one in the middle.
That's going to be in the middle, right? So go like this. And then number 5, is that bonded in the middle or at the end?
The one with the N.
At the end, also 3. 1, 2, 3. So then to finish, we would just fill in the hydrogens, which I'm not going to do because there's a whole ton of them. So that's what the structural would look like. If we were going to do the skeletal, we just make the 8 carbons. So we go 1, 2, 3, 4, 5, 6, 7, 8. This has a double bonded oxygen and a hydrogen attached. I think you include the hydrogen for an aldehyde, but I'm not certain. I think I've seen it both ways. So if you want to put the hydrogen there to represent an aldehyde, I'm fine with it. I've seen it with the double bond, seen it with the hydrogen there and without. So either way. So that's carbon 1, 2, 3, 4. So 4 is the isopropyl. So on that one, we go 1, oops, undo. Where's my undo? There we go. So in that one, we go 1, 2, 3. So it's to show that it's bonded to the carbon in the middle. And then on 5, we just do 1, 2, 3. So that would be the skeletal diagram. All right, let's do the next one. Ethyl butanoate. What is that? What kind of molecule is that?
Ester.
It's an ester, right? Awesome. That is an ester. And because it's an ester, which comes first? The alcohol or the acid?
Wouldn't it be the acid?
No, alcohol comes first. So the
Oh.
alcohol always comes first. And the way you can remember that is because when it says butanoate, that is also the name we would give the conjugate base of the acid, right? So if we had butanoic acid, when we took the proton off, it will become butanoate. So this is the acid part, second. So we have the alcohol comes first, and the carboxylic acid part comes second. So what alcohol do we have?
I'm sorry, why would the alcohol come first? Because based off of the chart you gave us, carboxylic acid always is number 1.
Right. So that's why the root of it is the carboxylic acid.
But then you just say that the alcohol goes before
Mhm.
the carboxylic acid?
Yeah, because in organic, the constituents come before the root.
Oh, okay. I thought you were saying vice versa, so I was. getting
No, no, no,
confused.
no, no. No, the constituents always come before the important part. So the important part here is the carboxylic acid, because that has preference. And then the alcohol comes before it.
Okay,
Yeah, I'm not saying that it comes before it in terms of importance or anything. I mean, it literally, when you're writing it down, the alcohol comes first and the acid is written second. So which alcohol do we have?
The eth- the ethyl.
Which alcohol is it?
The ethyl.
Ethanol, right. How many carbons does ethanol have?
2.
2, right. So we would just go 1, 2. And then we have an alcohol group. So I'm just going to leave the hydrogens out for right now. We'll put them in a minute. So butanoate, that's butanoic acid. So it's based on butane. So how many would that be? How many carbons is that?
4.
4 carbon.
4, right. So 1, 2. Let me do that in blue. So when we put them together, it'll make more sense. So 1, oops. So 1, 2, 3, 4. And I'm going to put the acid on this end. So when we join these two together, oops, I left out an oxygen. Someone should have pointed that out. So when we join these two together, I've got my alcohol and I've got my acid. What's the bond they make? It makes an ester bond, but what is an ester bond?
So it's just the carbonyl group.
So I got a carbonyl group. And what's connected to the carbonyl group?
Your oxygen.
An oxygen, right. So I've got an oxygen connected to the carbonyl. And then what's attached to this oxygen?
The alcohol.
The alcohol, but what atom on the alcohol is it attached to? Is it another oxygen? Is it this oxygen or
Carbon.
this carbon?
The carbon.
The carbon, right. So if I was to join these two, what is lost when you join an alcohol and a carboxylic acid together?
Hydrogen.
Not just
Water.
hydrogen,
Give up water.
water, right? You lose water. So you lose that, and then you just link those two together. So let's do that. What would that look like? So then I would have, let me do so I would have carbon, 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 double bond, O, and then C. So this would be the alcohol part, and this would be the acid part. And this is my ester bond right there. So then we just fill in the hydrogens. nothing there. Right, so ethyl, there's the ethyl part. And there's the 1, 2, 3, 4 carbon butanoate part. So if I was to do it in a skeletal form, I take my ethanol, which would just be and I would join it to my butanoate, which would be 2, 3, 4. And together, I would just get 1 O. Draw this. Like that. So 2 carbons on this side, 1, 2, and then 4 on the other side, 1, 2, 3, 4. Okay. Is that clear to everybody?
Yeah.
We're good? Okay. All right. So the next one is an amine. So what is the root for this one?
Butanamine.
Butanamine, right, that is the root. So how many carbons is that?
4.
4, just like butanoate, butane, it's got 4. So this has 4 carbons and it's got 2 constituents, a methyl and an ethyl. And where are the methyl and ethyl bonded to?
To the amine.
Nitrogen.
To the nitrogen, right. So how many things does the nitrogen have attached to it?
3.
3, exactly. Excellent. So let's do, so we've got a nitrogen, because that's basically an amine, is just a nitrogen with either carbons or hydrogens attached to it. So ethyl has how many carbon groups?
2,
2. And methyl is how many?
1.
1. So basically, all this is, it's just a nitrogen with 1 carbon, 2 carbons, 1, 2, 3, 4 carbons. So what else is going to be attached to the nitrogen? Is it going to have hydrogen?
I thought, doesn't the butanamine, isn't there a methyl in there, or did you already draw that in?
Methyl's right here.
Oh, okay.
And then the ethyl is here. And this is the butane part, butane, 1, 2, 3, 4 carbons. But my question is there anything else on the nitrogen?
Is that a hydrogen?
Then it would be charged. And there's nothing here that says it's charged. A quaternary amine would be charged. So if there was another carbon here, then it would have a positive charge on it. But it only has 3 things, only has 3 groups attached to it. So it doesn't have a charge. What would it have though?
Do you have to add a lone pair?
A lone pair, that's right. It would have a lone pair, exactly. Because nitrogen has 3, makes 3 bonds and has a lone pair. But in the skeletal part, we would not include, we don't include hydrogen, so that we wouldn't include a lone pair. So for the skeletal, we just put nitrogen. And then we have methyl, ethyl, and then 1, 2, 3, 4. for the butyl. That's it.
I was just wondering, I would think that the methyl group would be branched on the butanamine part. Why would that be wrong?
Because it has N-methyl here. If it said N-ethyl and then 3-methylbutanamine, then that would be carbon 1, 2, 3, and we would put a methyl group there. So then this would be a hydrogen. So that's what N-ethyl 3-methylbutanamine would look like that. But since N comes before the methyl, it's telling us that that methyl group is attached to the nitrogen. So if you
Okay.
so everything that has N before it, that's directly attached to the nitrogen. So we have an ethyl group attached, we have a methyl group attached, and then the rest of it is what else is attached to the nitrogen. Since it's an amine and it says butanamine, it's got to have 4 carbons attached to the nitrogen somehow. So we would remove this. Okay?
I have a question.
Yep.
For the structural for the ethyl butanoate,
Mhm.
should we have put the lone pairs for the ester?
No, you
No?
don't include lone pairs in the
Okay.
oh wait, in the skeletal?
In the structural, because
Not really. No, it's not really required.
but for the amine, you do need to have it.
No. I was just asking. Like
Oh, I
what
see.
I was just asking what would go there.
Oh, okay.
Is there anything else there? Yeah, and there isn't. There is a lone pair of electrons, but in the skeletal structure, we don't show them. It was just a general question, like, is there anything else attached? The answer is no. So would this be a primary, secondary, tertiary, or quaternary amine?
Tertiary.
Tertiary, right, because it has 1, 2, 3 carbons attached to it. That makes it tertiary. Good job. All right, so N-methyl hexanamide. So what is the base for this one?
Six carbon amide.
Right, we have a 6-carbon amide or amide. So 1, 2, 3, 4, 5, 6 carbons. So what does the amide mean? What kind of linkage is that?
Carboxylic and amine.
Right, so what should be on this attached to this carbon?
Double bond O
Yep, carbonyl, double bonded O, and what else?
and the nitrogen.
A nitrogen, right. That makes it an amide bond. So that's my hexanamide part. Where does the N-methyl come in? Where's the methyl group attached?
To the N.
The nitrogen, right? It says N-methyl. So that tells us that the methyl group is attached to the nitrogen. So we have 1, 2, 3, 4, 5, 6 carbons, an amide bond. So that's hexanamide. But the nitrogen that the hexanamide is bonded to also has a methyl group on it. So this nitrogen, would it have a double bond? Would it have a lone pair Would it have a nitrogen? Or a hydrogen? Would it have two hydrogens? What else would be attached to this nitrogen?
One more hydrogen.
Yeah, there would be a hydrogen there. And a double bond, and a lone pair. But we don't have to include the lone pair. So that's what that would look like. N-methyl hexanamide. We have an amide bond. And then if whatever's after the N, if there's an N there, that tells us there's something else attached to the nitrogen. We know the hexanamide's attached to the nitrogen because it's got to be, or it wouldn't be an amide. So that's what that would look like. And so for the skeletal, we just make 6 carbons. So 1, 2, 3, 4, 5, 6. Put a double bond there, and a line. And we're done. Okay. So that would be carbon 1, 2, 3, 4, 5, 6. So if there were any substituents on the hexanamide, we would say, 2, 3, 4, 5, 6, whatever it is. But if it's on the nitrogen, we say N. That just tells you where the substituent is. If there's a number, it tells you it's on the longest run of carbons. And in this instance, the longest run of carbons is the hexanamide. Okay. Next one, we have another amide. This time, a benzamide. So what's that going to look like? So I see benza again. So that already sort of tells us something. What's going to be the root of that when we see benza?
Benzene ring?
Hmm?
The benzene ring?
Benzene, right. We're going to start with a benzene ring. And you can put I just grew up with the 3 lines. You can put a circle in there if you want. It doesn't make any difference. Still looks weird to me for some reason, although it's more accurate. All right, so there's our benzene ring, and it has an amide on it. So how do we put an amide on a benzene ring?
So your benzene's your R group. and
That's
then
right.
you need
That's
a
right.
carbon
Mm-hmm.
with a double bond to oxygen. And then your other substituent is your nitrogen,
And then what else would be bound to the nitrogen?
a hydrogen,
Just one?
2 hydrogen, sorry.
2,
So
that's right.
NH2.
Excellent. That's right. So basically, yeah, this is amide is your functional group, and the benzene is just your R group attached to it. That's a really good way of looking at it. So we just take our functional group and we stick it on there. One thing to look out for is benzyl alcohol. That is not benzene with a hydroxyl group on it. What do we call benzene with a hydroxyl group on it? That's phenol, right? Benzyl alcohol is not the same. So what that is an extra carbon with a hydroxyl group on it. So that's benzyl alcohol. So the alcohol group, the hydroxyl group, is actually removed one from the benzene. With phenol, it's actually directly attached to one of the carbons on the
So
benzene.
in that case, then the phenol would be considered your substituent.
That's right. Yeah. So alcohol just says it's an alcohol group with a benzene ring attached to it. So an alcohol group is different from a hydroxyl group. An alcohol group actually has to have the carbon too. So that's different from alcohol is different from just the hydroxyl. So that is our benzamide root. So it also has a chlorine. And what's iodo mean?
Iodine.
Means iodine, right? So which one's carbon 1?
Amide.
That's where the amide is, right? So our carbon 1 has already been decided for us. This is carbon 1. So where is the chloro going to go?
At 3.
So 2 away from the amide group, right? So for
Yes.
grins, it doesn't matter which one we put it on. We can put it on there, or we can put it there. Either one makes no difference. They're both carbon 3. And where's carbon 4, where we put our iodine?
It's right next to it.
On which side?
On the sorry, I drew mine differently, so it'll
Right.
be
It's directly, but
Carbon
it's directly
4.
opposite the amide group, right? For some reason, a lot of people, there was a question on the exam about iodo, and a lot of people missed it. I don't know how. They just didn't put they drew everything else, so they didn't put the iodine in there. Maybe they just got confused to what iodo sounded like, a dodo bird or something. So again, for the skeletal, you have just basically exactly the same thing. Oops. The only difference is we don't put write the carb, we just go like this. That's it. That's the only difference. So not much difference between doing those two. When you're dealing with benzene rings, you draw it exactly the same way. Okay. Oh, I thought I had 2 more. Go back. Uh-oh. I thought I had 2 left. Let me see. Oh, no, that was it. Sorry. I thought I had 8 of them. Had 6. All right. So any questions about those?
Can I ask questions regarding the exam 3?
Yeah, for the next 7 minutes, you certainly may.
Oh, okay. So I was just wondering, so like aldehyde has an N group, right? And remember you said
Aldehyde is a what?
has a nitrogen, right?
No. Aldehyde is
Oh, my bad.
yeah, aldehyde
Okay, never mind.
is a carbonyl group with a hydrogen.
Okay, for the secondary alcohol, why would a 3-butanol be considered secondary?
Oh, where's my? See, so we've got, whoops. Oh, down here. So butanol. So what was it? 2-butanol?
Yes. Oh, you said 3-butanol is a secondary alcohol. Oh no, sorry. It's 3-butanol, a aldehyde.
Yeah, that is not, no, that's not an alcohol. It's an
Oh,
aldehyde.
my bad. 3-butanol.
Butanol, right.
Yeah. I was trying to figure out why it's secondary.
Because the carbon
Oh.
attached to it is attached to 2 other carbons.
Oh, okay.
Yeah. That's it. And the isopropyl is just this. It's basically, it's the same thing. That the hydroxyl group's attached to a carbon attached to two other carbons. So that's the same thing.
Can you go over number 2B, the IUPAC name? For the third exam.
All right, so here. So that was. 1, 2, 3, 4. A double bond there. And a methyl group there. All right, so it's just who would have, so we have how many, what's the longest run of carbons?
Four.
4, right. So you have 1, 2, 3, 4. So how many functional groups do we have?
2.
No,
Oh, I thought it was.
oh, no,
Isn't it
sorry. Yeah,
ketone
2,
and
I'm sorry.
alcohol?
No, I mean, how many constituents do we have? Sorry.
Oh. 1. Right, because the methyl group.
No, it's 3, right? There's 2 functional groups and another constituent. So that we have 1, 2, 3 different things that are attached to our 4 carbon chain. It's 3 different things. So who has the highest priority of those 3?
I believe it's the ketone, right?
Right, it's the double bond, it's the carbonyl. So we're going to start with that as the base. So we have 1, 2, 3, 4. So what are we going to call that?
Butanone.
Butanone, right. Butanone. So we have to say where the carbonyl is on the ketone, because it's either going to be a 2 or a 3. And we want to give it the lowest number possible. So what do we
B2.
give it? So we call it 2, right? And then we just say where the other constituents are in alphabetical order. So that's a methyl. And what do we call this one?
OL.
Hydroxy.
Hydroxy, right? Or hydroxyl. Or yeah, hydroxy, hydroxyl, either one. So the name is 4 hydroxy, 3 methyl, 2 butanone.
Oh, you couldn't just write OL.
No, because that is not the root. The root is the
Oh, I see.
butanone. So this is just
Oh, I see.
this is the
using
most important
prefixes.
functional group. So that gets the priority. Now everybody else is just a lowly substituent. So now we just name them in alphabetical order. And hydroxy comes before methyl. So it's 4 hydroxy, 3 methyl, 2 butanone.
So because it's IUPAC, if you did not alphabetize it, you would get dinged.
Yeah. Not much. I mean, it was worth 5, and I think I took off 1 or a half or something. Yeah. They did alphabetical order.
Professor,
Yeah.
I have a question about the worksheet number 12.
Okay.
Answer key.
Oh, I very well could have made a mistake on it. Let me.
Okay.
All right, let me pull it up.
The number 4, letter B.
12 key, where's the 12? Oh, there it is. So sorry, which one?
Actually, it's A and B. Number 4, A and B.
Number 4, A and B. Okay. Okay, what's the question?
So in the answer key, so for the A, so it
Mhm.
says 2-methylbutanamide.
Right?
So the methyl goes to the NH. Correct.
Oh, you were right. Yeah, I put the methyl in the wrong place. Yeah, nice catch.
And then
Yeah,
same
what
thing
it-
with letter B. The methyl should be carbon 4.
Oh man, you're right. Yeah, I'll put out a correction on those.
Okay, thanks. I just got confused. And I was
Oh
like,
man, yeah,
okay.
that's bad.
Thanks.
Yeah, I'll double check those online, but yeah, that would be N-methyl.
It should be
Three
N
bromo,
methyl.
right.
Okay,
Mhm.
got it. Thank
Yeah.
you.
Oh, thanks for pointing that out, man. Yeah, you can see when you're doing these at home with not enough coffee, these things can happen. So number 12, answer key. Yeah, because that'd be bad. So that's question 4, A and B. Thanks so much.
Thank you.
Okay. All right, I will correct that.
For four, I guess it's kind of hard to tell sometimes whether it's like the same molecule or a diastereomer or an enantiomer. So
Mhm.
like, how would you go about it?
All right, let me pull that up.
Like, I know it you know, when you superimposed it was the same. So it was like, okay, it's the same molecule. And then B, C, and D were a little bit tricky between whether they were the same or a diastereomer or an enantiomer.
Yeah, a lot of people had trouble with those. I think I've got it open here. Yeah. Okay. So A, can you see the question here? Can everyone see it?
Yes.
I think I'm seeing it, right. So A is the same molecule, and the reason for that is because you can stack these on top of each other. So here we go. So if I was to flip this around, it would look exactly like that. So I could stack those two right on top of each other, and they'd be exactly the same. Does that make sense?
Yeah.
Yes, those I could flip around. So the next one, these are pretty much all, why this one is a little tricky, because everything is in plane. This is planar. This double bond is planar. So everything is planar except one group, this one. And they're mirror images of each other, right? They're both going away from the plane. So I can't stack those two on top of each other. They'd be pointing in opposite directions if I was to flip them around. If I was to flip this one, then that hydrogen would be pointing out, while this one was still pointing in. So they don't stack on top of each other. So those are enantiomers.
Oh, so like if it had the wedge instead of the dash, then that would be considered the same molecule.
Yes, exactly.
Okay.
Yeah. But because if I flipped one, they'd still be pointing opposite. They wouldn't be pointing in the same direction. They'd be opposite to each other. So I can't stack those two on top of each other. Now the next one, we have 1, 2, 3 groups that are exactly the same, but one group that's different. So if I have 3 groups that are exactly the same and one is different, there's no way they're either they're not mirror images of each other, and I can't stack them on top of each other. They either all have to be different or they all have to be the same. If one of them is different and the other 3 are the same, then I can't do anything with them. Then they're not the same and they're not mirror images of each other. So that makes them diastereomers. And that's what you see with glucose and galactose. They're different molecules because they have all of their hydroxyl groups are the same except one. One of them's different. And so that screws up everything. That means they can't be identical and they can't be mirror images of each other. And that makes them diastereomers. And then the last one is the sort of similar to the first. Why this one's tricky is because that's planar because it's a double bond. That's planar because it's a double bond. So basically the only thing, and this is a ring. So basically the only thing that isn't in the plane is this group here.
Yeah, I thought that might have been enantiomer because
It is.
Oh wait, sorry. I thought that was a diastereomer because it was just that one that was different, right? So that's why I thought.
Right, it's just one that's different and they're mirror images. Sort of, one's coming out, one's going in. So they're mirror images of each other. Everything else is in the plane. The only thing that isn't in the plane is that one group. And it's a mirror image. So these are enantiomers.
And why would that not be like a diastereomer?
Because you've only one thing that's different and it's a mirror image. For this, you have 4 things, but only one of them is different. So there's no way to make either, you can't stack them on top of each other and they're not mirror images of each other. So
Oh, okay.
so they all have to be the same or they all have to be different. One or the other.
So Professor, letter
Yeah.
A, for example, if you flip for example, we changed the orientation. For example, the one on the left, you flip it all the way to the left.
Right, so if I flip this around, then I have, so if I just rotate it, basically rotate it
Mhm.
180 degrees, then instead of the hydroxyl group going in, it's now coming out. And the amine group, instead of going back, is also now coming out. And now it looks exactly like that. It's exactly the same thing.
But if
All I did was rotate it 180 degrees.
Would it be like an enantiomer if it was like one was a wedge and one was dashed, and then the other one was flipped where the other one was wedged and the other one was dashed?
just like letter D.
Well, what's different about D is that you basically, they had the difference between A and D. There's no sidedness here. I can, if I rotate this one, The only two things that rotate are these two. On the other hand, if I rotate this, let me clear out. If I rotate this one, what I get now so that looks the same. And this. So notice that this is no longer a mirror image. They're both pointing in the same direction. And this double bond is on the different side.
So if you can rotate
And the
it,
methyl group is on the different side.
so if you rotate it and it's the same as the other image, then that'd be an enantiomer.
If you rotate it all the way around and it's exactly the same thing, then they're the same molecule. And if you rotate it all the way around and it's different, it may be an enantiomer.
So I'm kind of confused. How is it not the same molecule?
Because this is pointing out, this is also pointing out. A mirror image has to be different. If one is pointing in, the other has to be pointing out. They have to be pointing either towards each other. So in a mirror, if I have my hands together and I turn them like this, either my thumbs are pointing toward each other or they're pointing away from each other. That's what the mirror image would be. I can't have this, right? I can't have that. They're either pointing toward each other or they're pointing away from each other.